So I'd like to thank Professor Sujata for the nice introduction and the organizers for inviting me to speak. So this is actually the very first time I'm giving a mini course of any sort. So I'm a bit excited and nervous, both at the same time. So as you can see, the title of my talk, the mini course is rather vague. It says Galois representations. And that basically means a lot of things. I mean, there are tons of things that can come under this title. So to clarify, what I'm going to do is I'm going to first give like a very brief overview of Galois representations that we are interested in. And then I'm going to move to Meso's theory of deformation theory of Galois representations. And later on, depending on how much time, so we'll go over the basics of Meso's theory. And depending on how much time we have left, we will talk about R is equal to T theorem and Gouvier-Mazur infinite Fern and pseudo representation, like these rather advanced topics. But I'm not, because I'm also new to this slide setup. So I don't know if the material I've prepared is too much or too less. So towards the end, we'll have to improvise whatever that is allowed in this slide setup. So the plan is this, that we will just take an overview of Galois representations, go into Meso's deformation theory, go over some basics, and then later on, depending on time, we'll take some directions that is suitable for us. So we are going to, and also I should say that we are going to stay away from proofs for a while. And whenever possible, I will give proofs. But for most of the parts, there will not be any proofs of like the various major results I recall. There won't be any proofs. But wherever it is practical to give proofs, I will give proofs. So our plan for today is we are going to talk about Galois representation, like an overview of Galois representation. So we'll begin with an overview of Galois groups whose representations we want to study. And then we'll move on to like examples of Galois representations coming from various number theoretic settings. So it's mostly going to be more or less like recalling various classical results and mostly example based. So most of the experts will already know most of this lecture. So I hope they will be patient throughout my first lecture. So let's begin. So Galois representations are basically representations of Galois groups. This is the most tautological statement that you can expect. But the question arises, which Galois groups? Galois groups of what field extensions, what we are going to study. And that's what we are going to do this, that we will first describe the Galois groups of interest. We'll make this sentence more precise. So we'll just give an overview of the Galois groups we want to study. So let's begin. So let K be a perfect field. So for example, a field of characteristic 0 or a finite field, and K bar be an algebraic closure of K. So we fix an algebraic closure, K bar. So if K double prime and K prime are finite Galois extensions of K inside K bar, and K prime is inside K double prime, we know that we have this surjective map from Galois K double prime over K to Galois K prime over K, just trivial restriction map. So you take an element of the Galois group of K double prime over K, you restrict it to K prime, it will give you an automorphism of K prime because K prime is also Galois over K. So therefore it will give you an element of Galois K prime over K. So this is just this restriction map, which we know is surjective, and we denote it by phi K double prime over K prime, right? So now these Galois groups of all the finite Galois extensions of K, which are in K bar, they are giving us an inverse system of finite groups. We have given the transition maps by this restriction maps phi K double prime over K prime. So using this inverse system, we define the absolute Galois group of K. So we define absolute Galois group of K to be GK, which is Galois K bar over K, which is the inverse limit of Galois K prime over K. The inverse limit is taken over all finite Galois extensions K prime over K. So the transition maps are the maps phi K double prime over K prime. So this is giving us an inverse limit, and the inverse limit is the absolute Galois group. So more, if you're not satisfied with this inverse limit definition, you want to be more explicit, we can say that the absolute Galois group of K, GK, it consists of these elements, the tuple GK prime, where for every finite extension Galois K prime over K, we have an element GK prime of Galois K prime over K at the corresponding slot corresponding to K prime. So it's a tuple GK prime where K prime varies over finite Galois extensions of K, such that when you have something in the K double prime slot, we call it GK double prime. And we apply this transition map phi K double prime over K prime, you get the element GK prime for all finite extension K prime inside K double prime. So basically it's a tuple where you have one slot each for every finite Galois extension of K. So for a K slot for K prime, we say the element is GK prime. And the property satisfied by this tuple is that whenever K prime is inside K double prime, the image of GK double prime under this transition map phi K double prime over K prime is actually GK prime. So this is the definition of inverse limit. I'm just putting it in words. And so the subgroup of this product group, which consists of all such tuples, that is the Galois group. So what we have is this absolute Galois group is actually an inverse limit of finite groups, which means by definition that it's profinite group. And it comes with a topology that I will now describe. So we equip all this Galois K prime over K by discrete topology. You know, they are all finite groups. So we give them discrete topology. And then we give this product K prime over K of Galois K prime over K, the product topology. So because each Galois K prime over K is compact, this product topology is also compact. And this GK, it's a subgroup of this product group. So we give GK the subspace topology, the topology coming from the product topology on Galois K prime over K, and each Galois K prime over K has discrete topology. So we will always view GK with this topology. So under this topology, GK actually becomes a topological group, which means multiplication map is continuous, inverse map is continuous, and so on. And therefore, we will always view this GK with this topology. So whenever I say absolute Galois group, you have to imagine the group with the topology. It's not just the group, but the group with this profinite topology. And some nice property is that under this topology, GK is Hausdorff, compact, and locally disconnected. Okay, so as we have this correspondence in finite Galois theory, whenever you have a Galois group of some finite Galois extension, the subgroups correspond to subfields. So in this case also, there is such correspondence, but the correspondence is between closed subgroups and subextensions. So basically, not all subgroups correspond to some subextensions, but the closed subgroups will correspond to subextensions. So this will already tell you why the topology is necessary, because already to give some like a basic correspondence like this, we need to involve the topology. Okay, and the correspondence is the same, a closed subgroup goes to the fixed field. That's the correspondence. Okay. So moving on, so this is so basically this is the Galois group. This is the absolute Galois group, and we are interested in studying this for number fields, or number field means finite extensions of Q. And for them, there is some additional structure which we'll now explore. So we specialize to the case of K is equal to Q. We are specializing this for K is equal to Q because that's what we are going to mostly use. And also, for the sake of being explicit. But this specialization, as we'll mention later, will work for any number field. So let's focus on the case K is equal to Q. For every prime P, we can choose an embedding iota P from Q bar to QP bar. So Q bar and QP bar are some algebraic closures of Q and QP. QP is the completion of Q by the periodic valuation, and it's called the field of periodic numbers. So if we choose an embedding iota P from Q bar to QP bar, we get this commutative diagram. So we have the canonical embedding from Q to QP. We have the canonical embedding from Q to Q bar, QP to QP bar, and we have this iota P, which makes this diagram commutative. Now, because of this diagram, because of the commutativity of this diagram, if I have an element of GQP, the absolute Galois group of QP, which is Galois group of QP bar over QP, you restrict it to Q bar via this iota P, you're going to get an automorphism of Q bar, which is fixing Q bar, Q. So therefore, this map iota P, it gives us an injection IP from GQP to GQ. Right? You take a automorphism of QP bar, which is fixing QP. You just restrict it to this Q bar over Q by this map iota P. It will take Q bar to Q bar. and therefore we get automorphism of Q bar, which means that we get a map from GQP to GQ. It's an injection. We denote it by IP, and it depends on iota p, right? Because we fixed an embedding, and that's how we got the map. So if you change the embedding, it's going to change this inclusion. But the good thing is that if we change the embedding iota p, the inclusion IP will change by conjugation by an element of GQ. You know why this is for the trivial reason that when you change iota p, what you're basically doing is that you're applying some automorphism of Q bar to itself first, and then applying iota p. So therefore, it's like, you know, you're first applying some element sigma of your Galois group, and then you are composing it with iota p to get a different embedding from Q bar to QP bar. So when you unravel everything, you get that you are basically getting the map that you get from GQP to GQ is just conjugation by this element sigma that you used initially to change iota p. So basically the key point to remember is that fixing an embedding from Q bar to QP bar gives you an injection IP from GQP to GQ, from absolute Galois group of QP to absolute Galois group of Q. It depends on iota p, but if you change iota p, this embedding, you know, it changes by conjugation by an element of GQ. So basically, you can view GQP as a subgroup of GQ, which is well defined up to conjugation. Now we can do the same thing for the completion at the infinite place. You know, you can choose an embedding I from Q to C, complex numbers. I from Q bar to C, the complex numbers, and we have this commutative diagram where you have this canonical embedding from Q to R to C, Q to Q bar, and Q bar to C. The embedding is shown by iota. And because of this, by the same logic, you get an injection from Galois C over R to absolute Galois group of Q, which depends on this choice of iota. So now this Galois C over R, we know it's very simple, right? It's group of order 2 is generated by the complex conjugation. And so therefore, we get a complex conjugation C in GQ, but it is only well defined up to conjugation because the same reason, right? Because we chose an iota, which gave us an injection from Galois C over R to GQ, which we denoted by I. Changing iota will change this injection by conjugation by an element of GQ. So we do have a complex conjugation, but it is again well defined up to conjugation. So the conjugacy class is well defined, but yeah, there are more than one, you can say. Okay, so this was the picture, right? So inside GQ we have a copy of Galois C over R, well defined up to conjugation, and a copy of GQP for every prime P, again well defined up to conjugation. And basically what we did, there's nothing special about Q. You can replace Q by any number field K. And you know, you replace QP by a number field, by a local field K math frac P, where the K math frac P is the completion of K at a prime ideal math frac P of the ring of integers of K. So using this, we get an inclusion, like the same logic, you know, in the previous commutative diagram, you just replace Q by K and QP by K math frac P. So we get an inclusion GK math frac P to GK, which is again well defined up to conjugation. Now, an interesting thing happens for the complex conjugation, because you may not have real embeddings of your number fields. You know, it could be totally complex and so on. But whenever we have a real embedding of the number field K, we can imitate the diagram that is given above. And so we get a complex conjugation, which is well defined up to conjugation for each real embedding of K. So every real embedding of K will give you a complex conjugation, which is well defined up to conjugation. So you'll get like R different, potentially different complex conjugations if your field has like R real embeddings. So they are not conjugate in your Galois group of GK, but if you go to GQ, they will all be conjugate. But over GK, they will not be, you know, so we have to like distinguish between them whenever we are over GK. So this is the basic picture that we want to study. So basically now we are ready to define Galois representations. So the main point to keep in mind is that for applications to arithmetic problems, we would like to study not just this absolute Galois group GQ or GK for any number field K, But we want to study the structure of GQ along with this conjugacy classes of homomorphisms, IP from GQP to GQ for every prime P. So in other words, we are obviously interested in the absolute Galois group GQ, but that's not the only thing that we are interested in. We are also interested in this whole package, as Mazur says in his notes, that we are interested in the whole package of this of GQ and this conjugacy classes of homomorphisms of the local Galois groups that we are embedding in the global Galois group. So we want to study this whole picture, not just GQ, but GQ and the conjugacy classes of homomorphisms IP from GQP to GQ. And for this purpose, the Galois representations come in handy, right? So if you want to study for this purpose, if you want to study this whole picture, it is natural to study representations of Galois group. It is natural to study representations of GQ because they do not distinguish between conjugacy classes, right? Or if I'm given a representation, the trace, the determinant, the characteristic polynomial is independent of conjugacy classes, right? If two elements are conjugate, and then their characteristic polynomial is same, trace is same, determinant is same. So sort of a representation is a thing which sort of sees beyond this well-defined up to conjugation. So that seems like a natural place to study. Those seem like a natural things to study in order to understand this whole picture. So keeping this in mind, we now define what we mean by Galois representation. So a Galois representation of GQ is a continuous homomorphism rho from GQ to GLN R for some positive integer n and a topological ring R. So there will always be some topological ring R, and if there's no topology, we'll say it has discrete topology. And the Galois representation will mean that it's a continuous homomorphism from GQ to GLN R. So as you can see already, we are dealing with rings rather than fields. That in usual representations theory, our representations are over fields, but here we will also be interested in studying representations over rings. So that the definition sort of reflects that. And okay, again, I should say that I'm restricting to GQ, but there is nothing special about GQ. You can do this for any any number field K, any finite extension of QP and so on. But most of the examples that we'll see, they will be over GQ. So that's why I am restricting myself to GQ. But usually a Galois representation means Galois representation of absolute Galois group of a number field, or some quotient of this absolute Galois group, or absolute Galois group of a finite extension of QP and so on. So it's a more general, what you can say, it's a more general phenomenon. But since throughout this course, we will mostly be restricting ourselves to GQ. So that's why I'm defining everything in terms of GQ for the sake of being explicit. Okay. So if we have a prime P, we have this inertia group IP inside GQP, which is like the inertia group at P. And we have this inclusion IP from GQP to GQ, right? We fixed an embedding from Q bar to QP bar, and that gave this inclusion IP. So using this inclusion, we can view IP as a subgroup of GQ, of absolute Galois group of Q, because GQP is a subgroup, so IP also becomes a subgroup. Again, this is well defined up to conjugation. But we say that a Galois representation rho is unramified at P if rho of IP is 1, which means the IP is in the kernel of rho. So now, as you see, the IP was only defined, well defined up to conjugation, right? But the thing is that being in kernel is independent of this well defined up to conjugacy, right? So this is indeed what you can say. This is indeed well defined. That some representation is unramified at P. This notion is rather well defined because the Galois group is because being in kernel is independent of conjugacy class. Okay, so we say that a Galois representation is unramified at P if rho of IP is 1. It looks like there's some messages in the chat, maybe. Okay, I don't think I can see them. Anyway. So we come to this important point, which is restricting the ramification. I will explain what I mean by that. So let S be a finite set of primes of Q along with infinity. We always include infinity in S for the sake of being easy. So let QS be the maximal algebraic extension of Q and ramified at primes outside S. That at all primes not belonging to S, this QS is, so the QS is the maximal unramified extension, which is unramified at all the primes which are outside S, which are not in S. And what do I mean by that? So basically QS is the composite term of all finite extensions of Q, which are unramified at primes outside S. So we know what it means for a finite extension to be unramified at some primes. So we take all the finite extensions which are unramified at primes which are not lying in S, and then we take its composite term and we get QS. We will call it QS. So because being unramified at a prime it's a property that is preserved by Galois automorphisms, right? So therefore, it is easy to verify that this QS is actually Galois over Q. And we denote GQS to be the Galois group of QS over Q. And this is basically, this Galois group is just the inverse limit of all finite, inverse limit of Galois groups of all finite Galois extensions of Q, which are unramified at primes outside S. So what we are doing here is essentially that we are basically putting all the inertia groups at primes which are not in S to be 1. So in other words, this GQS is the quotient of GQ by closed normal subgroups of GQ, which are generated by the inertia groups IL for all primes L not in S. So basically you are taking all the inertia groups IL for L not in S. You're taking the closed normal subgroup of GQ, which is generated by these inertia groups. So all inertia groups and their conjugates, everyone is there. And so GQS becomes a quotient of GQ under modulo this subgroup. So if rho is a representation of Q, which is ramified, which is unramified at primes lying outside S, then rho factors through GQS. So basically, this is trivial, right? Because if all the inertia groups are so the inertia groups IL for L not in S, if they're all in kernel, the closed normal subgroup generated by them is also in the kernel. So therefore, your representation will just factor through GQS. And in what follows, and in most of the Galois representations of interest, we will be focusing on such representations. We'll be focusing on representations which factor through GQS. Okay. So recall that we have this for a prime L, we have this exact sequence, right? You take GQL, you go modulo the inertia group, you get the absolute Galois group of the finite field FL. And this absolute Galois group is actually Z hat, which is just the inverse limit of Z mod and Z. This is all the standard theory. And this GFL, absolute Galois group of FL is generated by this automorphism, Frobenius automorphism of FL bar, right? So it is the automorphism of FL bar, which sends an element X of FL bar to X power L. And this is like this automorphism is like the topological generator of GFL. So we call this generator the Frobenius element at L, and we denote it by Frob L. Okay. So if L is not in S, you know that in GQS, the IL becomes trivial, which means that this embedding that we have from GQL to GQ, when you pass on to the quotient, we get an embedding from GFL to GQS, right? Because IL is becoming trivial. So basically we have this, so because of that, we have a Frobenius element Frob L in GQS for every such prime L, because the quotient is topologically generated by such an element. And again, this element is unique up to conjugation. This element is well defined up to conjugation, because our original embedding to GFL, it was well defined up to conjugation. Okay, so you have to keep this in mind that whenever I'm talking about this GQS and I take a prime L which is not in S, I'll talk about this element Frob L, and that will mean that it is the Frobenius element at L, which is coming from this embedding from GQL to GQ. Because we are going to GQS, we are going modulo IL, and that's why the Frobenius element also defines so the Frobenius element defines a well-defined element of GQS, well-defined up to conjugation. Now, if rho is a Galois representation of GQS or a Galois representation of GQ, which is unramified outside S, then for all L not in S, there is an element Frob L, as I just described, which is well defined up to conjugation. But whenever I say trace of row of Froebel or determinant of row of Froebel, that is independent of the conjugation, right? That doesn't see any conjugation or anything. So therefore, it does not depend on the choice of Froebel, and so it's well defined. So I can, whenever I have a Galois representation of GQS or a Galois representation of Q, which is unramified outside primes which lie outside S, then for any L which is not in S, I can always talk about trace row of Froebel, trace row of determinant row of Froebel. There's no ambiguity. It's all well defined. Okay, and one more important fact that I would like to recall is that if S prime is a finite set of primes of Q, then by Chebotarev density theorem, the set Froebel where L is not in S union S prime is dense in GQS. So basically, if you take the set of Frobenius for all but finitely many primes, this set is dense in GQS. So that's an important fact which will be used again and again later on for various purposes. Okay. So now we start with some examples of Galois representation. So the introduction got a bit extended than what I had originally planned. So we begin with the p-adic cyclotomic character, like the first example of Galois representation that we'll encounter. So let P be a prime n greater than or equal to 1 be an integer, and zeta p power n be a primitive p power nth root of unity in Q bar. So if you have an element sigma of the Galois group, it acts on this zeta p power n, right? It will take a zeta p power n to some other primitive p power nth root of unity. But since the group of p power nth root of unity is cyclic, we know that sigma of zeta p power n is actually zeta p power n power k sigma for some k sigma in z mod p power n z star, right? So this action, this gives us a character omega p power n from GQ to Z mod P power n Z star, which sends this sigma to K sigma. Yeah, because this is an action of the group on the roots of unity, we get a character which you denote by omega P power n. And all these characters are compatible, right? I mean, if you take omega P power n plus 1, you reduce it modulo P power n, you get omega P power n. So therefore, all these characters are compatible and they form an inverse system. So we can take an inverse limit of these characters and we get this character chi p, which takes values in Zp star. So chi p is basically inverse limit of all these characters omega p power n, which takes values in inverse limit of Z mod p power n Z star. This inverse limit is just Zp star. This is called the p-adic cyclotomic character. So this is like the very first example of sorry, is there? Okay. So taking this inverse limit, we get this character chi p from GQ to Zp star, which is called the p-adic cyclotomic character. So what are the properties of this p-adic cyclotomic character? First of all these finite extensions, the extensions that you get Q zeta p power n over Q, or the extension of Q obtained by adjoining zeta p power n, this is ramified only at P for all n greater than or equal to 1. So it follows that chi p is ramified P and unramified at all primes L not equal to P. So therefore, what we know is that because all these extensions are only ramified at P, all these characters omega p power n, they are all unramified at primes which are not equal to P. So therefore, this character chi p is also unramified at L not equal to P. And we know it is ramified at P because all these extensions are ramified at P. So that's the very first property, that this cyclotomic character chi p is ramified at P, but unramified at all primes L not equal to P. And because we know that they are not ramified at L not equal to P, we have this action of Frobenius at L on these roots. And if you take a prime L which is not P, the Frobenius at L, the Froebel, it takes zeta p power n to just its nth power for any n. So therefore, what we get is that for every prime L not equal to P, we have chi p of Froebel is L. So we know this character very well. We know which quotient through which it factorizes. We know what value it takes at all the Froebels. And so it's very nice. It's one of the nicest example and one of the very first example that we see. And we also know that the character is odd which means that chi p of complex conjugation is -1. This is also very easy to see because all these roots are not real. All of them are complex numbers. So the complex conjugation, it acts non-trivial. Okay, so this is the very first example, p-adic cyclotomic character. And this will make an appearance again and again later on, in connection with whatever, with the things that we are going to see. Okay, let's move on to the next example. Our next example comes from elliptic curves. So we talk about p-adic Galois representation attached to an elliptic curve. So E be an elliptic curve over Q, P be a prime, and we denote the Q bar valued points of E by EQ bar. So you take all the points of E which have coordinates in Q bar, we denote them by EQ bar. So we just saw in the previous lecture that E is an elliptic curve, and then we have this multiplication by P power n map for every integer n greater than or equal to 1. So we denote this isogeny by bracket P power n, and we define EP power n to be the P power n torsion points of EQ bar. What does it mean? It means all points in EQ bar such that P power n times P is 0. They are really the P power n torsion points. It is easy to see that this action of GQ on EQ bar, it preserves EP power n because the elliptic curve is defined over Q. So all these addition laws and everything that is defined over Q. So this multiplication by P power n isogeny is also defined over Q. And because of that, whenever you have a torsion point like this, you apply an automorphism of Q bar over Q, it will still give you a P torsion point, a P power n torsion point. So we have an action of GQ on this EP power n, it preserves EP power n. So because of this action, we get a homomorphism from GQ to GL2 of Z mod P power n Z, where I missed telling this thing that it is well known that this EP power n is actually isomorphic to Z mod P power n cross Z mod P power n. So it's a free Z mod P power n module of rank 2, because of which this action gives us a continuous homomorphism from GQ to GL2 of Z mod P power n and Z. So, and we denote this by rho E comma P comma n, or rho EPN. Okay, and again, this is a very nice, system of representations, because you take rho EPN plus 1 and you go modulo P power n, you get rho EPN, just like the way we had in a p-adic cyclotomic character. So therefore, this is like a nice system of representations. So it gives us an inverse system of representation, and we can again take an inverse limit in the same way that we did for p-adic cyclotomic character. So we take the inverse limit of these Galois representations, and we get a Galois representation rho EP, which is an inverse limit of rho EPN. So it goes from GQ to inverse limit of GL2 of Z mod P power n Z, and this inverse limit is actually GL2 of ZP. So therefore, we get like a p-adic representation. We had this mod P power n representations, we took inverse limit, and we got a representation over ZP, and we call this the p-adic Galois representation attached to the elliptic curve E. Okay. All right. Now some properties of this. The first property we would like to note is that the determinant is chi p. Now the determinant of this Galois representation rho EP is chi p, which is like the p-adic cyclotomic character that we just saw, on the previous slide. And so this means that rho E comma P is an odd Galois representation, because the determinant of rho E comma P of the complex conjugation is -1. And the representation is also ramified at P, right? Because the cyclotomic character is ramified at P. So the representation has to be, if your determinant is ramified, then your representation has to be ramified. The inertia group cannot be mapped to a trivial element under rho EP, because the determinant of inertia is not 1. So it's like a very trivial sentence. Another property is that the representation is absolutely irreducible. So we would like to know if there are some other properties or not, right? We would like to know if at what primes this rho EP is ramified, or at what primes it is unramified. In the p-adic cyclotomic character case, it was rather easy to see, where it was ramified and where it wasn't ramified. So we were talking about We were dealing with like just the abelian extensions of Q, which we knew very well. So it was all like very easy. But here the description is not so simple, right? We don't know what this fields of Q are, which are cut by p power n torsion points. And so we would like to know where it is ramified and where it is not. And that's where we have this criteria by Neronov-Sheffervich, which implies that if L is not equal to P, that's a prime, then the Galois representation is unramified at L, if and only if E has a good reduction at L. Good reduction means that when you reduce this elliptic curve modulo L, you still get an elliptic curve. You don't get any singularity. So the criteria of Neronov-Sheffervich tells us that for all primes P not equal to L, the representation rho E comma P is unramified at all those primes L where it has good reduction. And if there is no good reduction, then the representation is actually ramified. So because there are modulo all but finitely many primes L, the elliptic curve has good reduction. So this is again a representation which is unramified outside a finite set of primes. It's again a representation of GQS, the terminology that we had introduced. So if L is not equal to P is a prime at which E has good reduction, we denote by EL bar the reduction of E at L. So this is the elliptic curve that we get by reducing modulo L. Okay, so the recipe is a bit complicated. You go to QL, you get like the minimal Weierstrass equation, you reduce it modulo L, and that's what we'll call EL bar. But I'm skipping all those details. So why did we introduce this notation? Because now we are going to see what is the trace of this representation at Frob L. So the trace of this representation at a prime L where we have good reduction, the trace of rho E comma P at Frob L is L plus 1 minus the number of points of EL bar over FL. So it's rather a nice thing. This representation is sort of encoding the information about reduction of elliptic curves at primes of good reduction. It is knowing this representation tells you something about the number of points, for example, of EL bar. So that way it's like the representation is really intimately connected with arithmetic properties of elliptic curves. It's not something that we just cooked out of air. It is really intimately related. And I hope this expression for the trace, it convinces you that. Okay, this is like one of the interesting facts that why we want to study Galois representations attached to arithmetic objects, because they do encode some interesting arithmetic information. So more generally, if we have an abelian variety A of dimension G over a number field K, we know that this P power n torsion points are of the form Z mod P power n Z over 2G power 2G. So it's like a free Z mod P power n Z module of rank 2G. And the Galois group acts on this P power n torsion points, and it gives us a Galois representation rho A P n from GK to GL to G of Z mod P power n Z. We can again take the inverse limit of these, and we get a periodic Galois representation rho A attached to the abelian variety, which goes from GK to GL to G of Z. So basically this elliptic curve, the Galois representation attached to elliptic curve, it was like a very special instance of a general phenomena. And the phenomena being that if you have an abelian variety of dimension G over a number field K, we know how the torsion point, the structure of torsion points, and taking the Galois action, taking the inverse limit, we get a representation from GK to GL to G of Z. And when you specialize it for an elliptic curve over Q, we get what we get the periodic Galois representation attached to an elliptic curve. Again, both these constructions that we saw, periodic cyclotomic character and this Galois representation, they can be done over any number field, any finite field of QP and so on, a finite field extension of QP and so on. We're just sticking to GQ because that's what we are, that we'll be focusing on for most of the course, for simplification. Okay, now we come to the next important set of examples, and they come from Galois representations attached to modular forms. So I'm nearing the halfway mark. So if there are any questions, maybe the organizers can tell me if there are any questions that I should address before moving on.
Yeah, well, there doesn't seem to be any question. There was one which was already answered in the chat.
Okay, okay.
So, but maybe it's a good time to pause and ask the audience if they have any questions. Let's say we allot 5 minutes for questions.
Sure, sure. Yeah. When.
So somebody has raised a hand.
Okay.
So maybe.
Please ask the question. Raise the hand.
So we need to unmute. So maybe.
Oh, so can somebody take charge of that unmuting?
Yeah, I'm unmuting.
Do you hear me?
Yeah.
Yeah. In fact, I have two questions about last slide.
Mm-hmm.
The first one, if possible, please. In the middle of a slide, you said that the trace of Frobenius is L plus 1 minus the number of elements of EL over FL.
Yeah.
Two questions. One, what is the generalization of these for abelian varieties?
Mm-hmm.
And second is, what about P? Frob at P is not a well-defined element, but it is a conjugacy class.
No, so basically, see, the Frobenius element is only defined when your representation is unramified, but at P, your representation is ramified. So, so like the trace at Frob P doesn't make sense because the element Frob P is not well defined, not even up to conjugacy. No, it's only well defined whenever we go to, whenever something is unramified, that's when this Frobenius element is defined. But at P, it is not well defined because at P, the representation is ramified. So it doesn't make sense about trace of Frob P. And about abelian, it's a good question. Unfortunately, I don't know the answer at the top of my head. But it's a standard. I mean, you can just search for Galois representations attached to abelian varieties. I am not sure if there is a clean answer like this, but I'm pretty sure that you will get some answer. Unfortunately, I don't know the answer at the top of my head.
Oh, thanks. So you said that there is a formula for the trace in the case.
I believe there must be. I'm not, again, as I said, I'm not entirely sure, but there must be something nice that is known.
Yeah. Thank you.
It may also depend on the type of abelian varieties and so on, because that theory is much more complicated than the theory of elliptic curves.
So maybe you can continue.
Sure. Yeah. So let's continue to the next, as I said, the next important examples, which are p-adic Galois representations attached to a modular eigenform. This is like the most, you can say, like the most famous set of examples, or the most well-studied set of examples after elliptic curves. So let F be a modular eigenform of a level gamma 1 of n and weight k greater than or equal to 2. So by that, I mean F is an eigenform for Hecke operators TL and a diamond operator L for all primes L not dividing n. So basically, if you want to keep an example in mind, that will be the Ramanujan's delta function. So if you take F to be the delta function, which is some tau n q power n, n goes from 1 to infinity, and tau is the Ramanujan's tau function. It's an eigenform of level 1. So n is 1 and weight is 12. So k is equal to 12. So that's an example you should keep in mind, maybe just for the sake of, for the sake of understanding throughout this example. So it will help a lot. So let epsilon f be the Nebentepers of f. So the Nebentepers of delta is just trivial character. For a prime L naught dividing n, we denote by ALF the TL eigenvalue of f. And KF be the extension of Q, generated by the set of Hecke eigenvalues of f over Q. So for delta, this extension is just Q because all the eigenvalues of delta are integers. So KF, as it's well known, that it's a finite extension of Q, and we denote its ring of integer by OKF. Okay, so so I'm developing some piece of notation which will go into this main theorem that we'll state later on. So it's maybe a bit too hard to keep track of, but again, as I said, you can keep the example of delta in your mind. So a delta, K delta is just Q, so OK delta is just Z. Let P be a prime, mathfrak P be a prime of OKF, which is lying above F, and mathfrak OKF P be the completion of OKF P. some more notation. And since every prime L not equal to P is invertible in OKF mathfrak P, we can view epsilon F as a character taking values in OKF mathfrak P star using this recursive relation between Hika operators. We'll tell you that the values of epsilon F, they all are inside the group of units of OKF mathfrak P. Okay, so this is all some standard mumbo jumbo or standard notation. So this, why did I state this? To state this main theorem, which is due to Eichler, Shimura, and Delin, which tells us that to every modular eigenform F, there is a Galois representation attached to it. I will say what that means, so it will be more clear. So let F be a modular eigenform of level gamma 1 of n and weight a greater than or equal to 2 with the nebentibus epsilon F, as we just said. P be a prime, mathfrak P be a prime of OKF lying above P, and S be the set of primes which divide n, and we include P and infinity as well. We don't know if P divides n or not, so we include it for our sake, and also infinity. So in this setup, there exists a periodic Galois representation which we denote by rho f from GQS to GL2 of OKF mathfrak P, such that the determinant of this representation is epsilon f times cyclotomic character power k minus 1. So it's epsilon f times chi p power k minus 1. And trace rho of Frobel is actually ALF, the TL eigenvalue of f for all primes L not dividing NP. Moreover, this rho f is absolutely irreducible if and only if f is a cusp form. So basically, this theorem is telling us that for every f, there is a Galois representation, and we say that the Galois representation is attached to f because of this relation of trace of rho of Frobel is AL of f. So there is a direct relation. This Galois representation is encoding the information about Hecke eigenvalues of f. So that's why we call it like the trace of rho of f of Frobel is ALF. This relation, because of this, we say that this Galois representation rho f is attached to f. That's the relation between f and rho f. And we know that the rho f is absolutely irreducible if and only if f is a cusp form. So if you have this example of delta in your mind, then this theorem says that we have a representation rho f from GQ to GL2 of ZP for every prime P. This representation is unramified at all primes which are different from P. The determinant is just cyclotomic character power 11 because K is 12. There's no nebentibus. And trace of rho f of Frobel is just tau of L, the Ramanujan tau function for all L not equal to P. And the representation is also absolutely irreducible, which means it is absolutely irreducible as you go to QP bar. So I hope the statement is clear. You may have seen some other formulations, but they are all same. All of these are the same formulations. So basically, the upshot is that to every modular form, there is a periodic Galois representation attached to it, whose properties are as listed. Some comments on this. So basically, if your F is an Eisenstein series, it's easy to attach this Galois representation. It is a reducible Galois representation. And from the coefficients of, from the Hecke eigenvalues of Eisenstein series, which we know very well, you can just say that there are some two finite characters, chi1 and chi2, and this representation could be chi1 direct sum chi2 times chi p power k minus 1. So for example, if you have an Eisenstein series of, say, level 1 and weight k, this representation is just 1 direct sum chi p power k minus 1. So for E4, the representation is just 1 direct sum chi p cube and so on. So for Eisenstein series, this construction is not difficult. The difficult part is for the cusp forms. So Eichler Shimura did it using, they were the first people, they first did the case of k is equal to 2. They used this Jacobian of the modular curve of level n, and they used it, they used this geometric argument to get such a representation. But they were only doing it for k is equal to 2. Their method did not work for k greater than 2. And then Delin used Étale cohomology to get this representation for k greater than 2. So this was like a very involved argument, rather a difficult argument, you can say. And they both use geometry very freely. And this geometric argument doesn't work for k is equal to 1. So that's why I have not included it here. I will say later on what happens for weight 1 modular forms. But yeah, so one question that you could ask is, okay, you have given us a representation. Is this representation unique? Because all I've said is that there is a representation. I have told you what the traces are. And I've told you if it is absolutely irreducible or not. But it's not clear if it is unique or not. You know, if it is reducible, it need not be unique, right? Because it could be a sum of 2 characters. You can also take an extension of characters, you know. So upper triangular with the triangular entry not 0 and characters on the diagonal. And that will also have the same characteristic polynomial. So if the representation is attached to an Eisenstein series, such a representation is not unique at all. But if it is attached to a cusp form, we know it is absolutely irreducible. And we know the trace and determinant. So we know the characteristic polynomial at all Froebels for L not dividing NP. And these Froebels, they are dense in GQS. So because of that, we know like the characteristic polynomial of every element of GQS. So if there are 2 such representations, their characteristic polynomials are going to be same for every element. So when you go over QP bar, Brouwer-Nesbitt theorem tells us that such 2 representations have to be isomorphic. So the upshot is that if F is a cusp form, such a representation is unique as long as you go to QP bar. If you don't go to QP bar, then we don't know. Like for example, there could be different lattices that you can choose, which are not conjugate to each other over OKFP, but when you go to QP bar, they will be conjugate to each other. So basically when F is a cusp form, there is such a representation is unique over QP bar. So, but not unique over GL2 of OKFP. So over, let's say if you are in the case of delta, there could be more than one lattice. So there could be more than one representation over GL2 ZP, which has this property, and they are not isomorphic over ZP, but you go to QP bar, they become isomorphic. That's the point of the uniqueness. So the thing to keep in mind, if F is a cusp form, such a representation is unique over QP bar. So if I give you 2 such representations, I know they are isomorphic over QP bar. But if you ask me over some subring or over ZP, then they need not be isomorphic. So this is just a minor technical point that I thought I should point out. Okay, so this is basically the main theorem in the theory of these Galois representations attached to modular forms, which tells us how there is a representation and what properties it has. Now, we make a very simple observation. Suppose F is a cusp form. So we know it comes from a new form of a potentially lower level, right? So let G be the new form which gives rise to F. Because we know that F is a cusp form, we know that there is a new form G of some level M which divides N, such that F is just some GQ power some K for K a divisor of M over N. You know, F itself could be new or not, we don't know. But all we know is that there is a new form underlying F which is giving rise to F. And because the theorem says that to any eigenform, there is a Galois representation. So there is also a Galois representation attached to this rho G, but G is a new form. And level of G divides N. So we can consider rho G as a representation of GQS, right? Because the S contains the primes which divide N, and because G divides N, we can, so the representation attached to G is unramified at even more primes, right? It is unramified at primes which don't divide its level. So there could very well be primes which divide N but don't divide the level of G. So anyway, we can consider rho G as a representation of GQS. And for every L not dividing N, the TL eigenvalues of F and G are the same. Means that trace of rho F of Froebel is trace of rho G of Froebel for all primes L not dividing NP. Right? So again, we are getting 2 representations of GQS whose trace and determinant coincide for a dense subset of GQS, right? For all Frobeniuses which do not divide NP. So by Chebotarev density theorem, we know that this set is dense in GQS. So basically the trace of 2 representations is same, and And determinant is also same. So as the Brouwer-Nesbitt theorem I quoted, we get that rho f should be isomorphic to rho g over qp bar, because rho f is absolutely irreducible. So because they are isomorphic over qp bar, the ramification properties tells us that if m is the level of G, then rho G is unramified at primes not dividing M. So we get that rho F is also unramified at L if L does not divide MP. So basically, why did I show all this calculation? So the upshot is that even though we know that the representation attached to F is potentially, it could be ramified at a prime L dividing N, this tells us that there might be some primes which divide N at which the representation could be unramified, because you already have a form of lower level whose representation is same as the representation attached to F. So you know, the unramified statement that we made is not really optimal, because you know, it could still be unramified at more primes than what we had listed, as this calculation shows. So that's the point I wanted to make. Now we come to the case of weight 1, which was done by Delin Ser. So let F be a modular eigenform of level gamma 1 of n and weight 1 with Nebentupus epsilon f. Again, S be the set of primes which divide n, and we also include infinity. Note that we have not taken any p. If you see, the p-adic representation and p were like prominent in all our examples before, but in this case there is no p yet, and you'll see the reason why. Then there exists an odd Galois representation rho f from GQS to GL2 of C. So we get a representation over complex numbers such that determinant of rho f is epsilon f. There is no other component for the determinant. You know, determinant is of finite order. So that's why there is no p in the picture, because no p-adic cyclotomic character. And trace of rho f of Rob L is AL of f for all primes L not dividing n. So this theorem is very much similar to the theorem of Eichler, Shimura, and Delin that we just saw, but the difference is that here the representation is over C. You know, there the representation was over some extension of ZP, right? So what we did was we chose a prime, and for every prime P, we had a representation which was defined over some finite extension of ZP or over ZP or whatever. But here we are not choosing any prime. You know, we are given a form, we are giving you a complex representation. There is no prime and nothing in the picture yet. So that's why this case is rather different from the case of k greater than or equal to 2. And they use this so the congruences of modular forms and the Galois representation attached to a higher weight modular forms and so on. So it's a nice paper to read actually. So maybe we should recall some more properties of this. So again, a key property is that if the F is weight 1 form, then rho F is absolutely irreducible, or here we are over C. So it's irreducible if and only if it's a cusp form. Again, the construction is only challenging for cusp forms. For Eisenstein series, it's easy, as I said, you know, it's just a sum of 2 characters of finite order. So the construction is really challenging for cusp forms. So suppose, you know, and again, we can use the same argument we saw here, right? That if F is a cusp form and G is the new form which is giving rise to F, the same argument that we saw in weight k greater than or equal to 2 tells us that the Galois representation attached to rho G is same as Galois representation attached to rho F. You know, they are isomorphic. So if M is the level of G, rho F is unramified at all primes L not dividing M. So again, the ramified statement that we make, it need not be optimal, because you know it all depends on what the level of underlying new form is. Now, this GL to C, it has so the representation is continuous. The GL to C, the topology on GL to C is not like the p-adic topology or the profinite topology that we have on Galois group. You know, so basically we have a neighborhood of 1 which does not contain any non-trivial subgroups. GL to C, it has a neighborhood of 1 which does not contain any non-trivial subgroup. Therefore, kernel of rho F, this is an open subgroup of GQS, but an open subgroup of GQS and GQS is compact, which means that the image of rho F is actually finite. So this is like a typical weight one phenomenon. It's special to weight one that the image is actually finite because of the topologies involved, because we have a complex representation and not a periodic representation. So this is already like something very unique and different. For weight k greater than or equal to 2, you never have finite images, right? Because the determinant has a cyclotomic character component and that has infinite image. So your representation can never have a finite image. But in weight 1, we do have finite image. So this is something already very interesting that distinguishes this case from previous cases. And they already proved that the image of this representation in PGL2C, when you go modulo scalars, it's a solvable subgroup of PGL2C. And we know what solvable subgroups of PGL2C are. From that, we get that the projective image of rho f is either A4, S4, A5, or D2n, dihedral group with 2n elements with n greater than or equal to 3. So we know this, like the image of representations, very nicely and so on. And because this representation has finite image, you can view it as a representation over Q bar. You can conjugate it and make sure that the representation takes values in GL to Q bar. And for every prime P, we have fixed an embedding iota P from Q bar to QP bar. So you can view rho f as a periodic representation, right? So you can view it as a representation over GL to QP bar. And you get a statement which is similar to the statement we had for k greater than or equal to 2 prime, k greater than or equal to 2 weight. So basically the point is that here there's no family, or there's no compatible family of Galois representations. There's only one representation, and then we view the same representation over QP bar for various P. But the representation to begin with is same. So over Q bar, and using the embedding, we view it over QP bar. But otherwise, there's no. So that's the only difference. Because there for every prime P, we have a different representation. Here, sort of the underlying representation is same. We are just changing the coefficient field. So that's the difference between weight 1 and weight greater than or equal to 1. Okay. So it looks like I'm going slower than what I had expected. So let's see if I can finish off all the slides I have, or I may have to stop in between, but let's see how far we can go. So we said, right, that we wanted to study not just the Galois group, but how these other groups also sit inside our Galois group, right? And when I said, so when I gave this theorem about Galois representations attached to modular forms or elliptic curves, I told you what happens at primes L, which do not divide the level of modular form, right? The representation is unramified. We know the trace of the rho f of Rob L because it is the TL eigenvalue of f. We know the determinant. So really the question is, what happens at L dividing n? What happens at those primes, L dividing n? And for that, we need to go into something known as well-dealing representations. Now this, I'm going to go a bit fast because we don't have enough time, and I already had not prepared. So I had prepared this part like in very brief. So because I wanted to go fast, because if I give all the details, it will take a lot of time. So I'm going to go a bit fast over this. We have this exact sequence from IL to GQL to Z hat, right? That we just saw. You go modulo this GQL, modulo IL, and you get the absolute Galois group of FL. We denote the quotient by F, and we define something known as the Weyl group. So the Weyl group is all elements of GQL, so that f of g lies inside Z. And we will now give this Weyl group a topology. But the topology is not the subspace topology coming from GQL. We give it a topology such that the inertia group subgroup is open in WQL, and the subspace topology on the inertia group, which is coming from WQL, is same as the subspace topology coming from GQL. But and we want WQL, like the multiplication by G map on WQL, to be homeomorphism. These two requirements give it a topology and makes it a topological group. But this is not the subspace topology on WQL, which is coming from GQL. And a well-dealing representation is the following. So if you have a finite extension L of QP with the P not equal to L, a well-dealing representation of WQL over a finite dimensional L vector space V, it's a pair R comma N such that R is a representation from WQL to GL of V, So continuous representation, but with discrete topology on GL of phi. We're not giving the p-adic topology, we are giving it the discrete topology. And N is an endomorphism such that R of G times N times R of G inverse is L power F of G times N. So a Well-Deligne representation is a representation over some finite dimensional L vector space and an endomorphism N. So R is continuous, but with discrete topology, and IL is compact. So this already tells us that the image of IL under R is finite. Now this seems like a bit of, it seemed to come out of air from nowhere. So I'll explain the relevance now. That if you have say you have a representation rho from GQL to GLN of L, continuous representation, but we are giving p-adic topology on L. So after conjugating, if necessary, we can assume that this rho actually takes values in GLN of OL, the ring of integers. Because the GQL is compact, we can use some standard argument to get a lattice, which is stable by this action. And so we get a representation from GQL to GLN of OL, where OL is like the ring of integers of L. But now this GLN of OL is rather special group, right? We go modulo the uniformizer, we go to GLN of its deciduous field. Let's call it F. So we have this map from GLN of OL to GLN of F, where we are just going modulo the uniformizer. And the kernel is a pro-P group. Now inside our inertia group, there is an important and a big subgroup called WL, the wild inertia group. Is the pro-L silo subgroup of IL. Because it is pro-L, it cannot get mapped non-trivially to a pro-P group, right? And here in GLN of OL, we have a pro-P group, which is a finite index. So as an upshot, what we get is that rho of WL is finite. So this inertia group, which causes all the havoc, this image becomes finite. So that is very nice. So we can just go to a finite extension K of QL, and rho of IK can be assumed to be unipotent. Because you can just take a finite extension so that this rho of IK will lie inside this pro-P subgroup, and then we can take another finite extension so that it becomes unipotent. And because it is unipotent, we have this exponential map coming from Mn of OL to this unipotent, to the identity plus L square times Mn of OL. Something which is very similar to the exponential map coming from ZP to 1 plus PZP. That exponential map, it can be described in a nice way. So basically, if you have this composition from IL to IL modulo WL to ZP, so you go to the ZP quotient of the tame inertia group, denoted by phi L, and if you fix a lift sigma of Froebel in GQL, we get a matrix N in Mn of L, such that rho of G is exponential of phi L of G times N for all G in IK. So basically, the upshot, what I wanted to say, is that there is a finite index subgroup IK inside IL, so that the rho is described in this nice way. The rho of G is actually just the exponential of phi L of G times N for some fixed N. So there is an N like that. So what happens is that if you take R from WQL to GLNL to be this representation, R of G is exponential of minus of phi L of sigma power minus NG times N times rho of G, then R comma N becomes a Well-Deligne representation, which is bounded. So that determinant is in OL star and characteristic polynomial is in OLX for all G in WQL. So basically we started with a p-adic representation. We knew that this inertia is causing havoc, but which usually causes havoc, it has finite image. So therefore, we have this nice description of the representation in terms of exponential map and the matrix N, which we get here, exponential of phi L of Gn. So we just multiply by the inverse of this and we get a representation of the Well-Deligne. So what I have done, I have taken a p-adic representation of GQL. I have given you a Well-Deligne representation. And the Grothendieck monodromy theorem says that this construction is actually a bijection between isomorphism classes of rho from GQL to GLN QP bar and of n-dimensional bounded Well-Deligne representations of WQL. So basically, a Well-Deligne representation a bounded Well-Deligne representation will give you an p-adic representation of GQL and vice versa. And well-dealing representations are much easier to study, right? Because, you know, the topology is nice and image of inertia is finite and so on. So they are like the easier things to study. And another good thing that they have is that they feature in the local Lagrange correspondence. So that's what I'll say next. So I was too quick on this part, but that's because, you know, if I start explaining everything, it is going to take a lot of time. So the takeaway from this part should be that when L is not equal to P, the wild inertia group, it does not, what you can say, it does not play an important role. The image is finite, so we are controlling the wild inertia group. And once you go modulo wild inertia group, we know everything very well. You know, we know tame inertia group, we know how Frobenius acts on it. So that is really the, like, once you go modulo wild inertia, everything is nice. And you can actually describe the representations explicitly. But the only thing is that we don't, if we don't know what happens at wild inertia, you cannot do that. But the good thing here is that when L is not equal to P, the wild inertia is not causing many problems. You know, it is only giving a finite image. So what happens is that I mentioned local Lagrange. Why did I mention it? Because to every modular eigenform F, you know, you have this automorphic representation attached to it. So you can take the L component of that, pi FL. It's an automorphic representation of GL2QL. Local Lagrange correspondence gives us from this automorphic representation pi FL, it gives us a periodic Galois representation of well-dealing group. And from that, you get a periodic Galois representation of GQL from whatever I just mentioned before. And Carayol proved that this representation is same as this rho f restricted to GQL. So you have something from the automorphic form side, you use local Lagrange to get it to Galois side, and it turns out that it is actually what we wanted. You know, we wanted to know what rho f restricted to GQL is. And it turns out that this recipe is actually gives us that. And this automorphic side is well studied. So you know what this automorphic representation can be. So you know what this well-dealing representations can be. So no, there are only 3 or 4 possibilities of what this rho f restricted to GQL can look like. So let me mention that. It's a theorem due to Carayol and others. That if F is a new form of level gamma 1 of n and weight k greater than or equal to 1 with Nepenthes epsilon f, let rho f be the periodic Galois representation attached to F as above. If L divides n, then this representation is actually ramified at L. You know, we like initially we saw for eigenforms, this is not true, right? Because the underlying new form could be of a lower level. And then you will get some primes which divide the level of F, at which the rho f is not ramified. But when you have a new form, the rho f is always ramified at L. Moreover, we can also describe rho f restricted to GQL. So it is one of the following. It is either a sum of 2 characters where at least one of the characters is ramified at L, both could be. This is the principal series case. Or it's an extension of chi by chi times chi p, the periodic cyclotomic character, and a non-trivial extension. So basically it looks like chi times chi p star 0 chi, and star is non-zero, and chi is some character. Or it could be, so this was the Steinberg case, like the extension of chi by chi p, that was the Steinberg case. Or it could be induced from a character of a quadratic extension f of QL. Let's say the character is chi and rho f restricted to GQL is isomorphic to induction from GF to GQL of chi. This is like a dihedral representation, you can think of it. So this is like the supercuspidal case. And there's one more case remaining when L is 2. So this can only happen when L is 2. And the projective image of inertia group at 2 is either A4 or S4. So basically, because this theorem is also telling us potentially what can happen at primes dividing n. We already know from previous theorem at what can happen at primes not dividing n. That it is unramified, we know the trace, we know the determinant. So we sort of know what representation looks like. And this theorem tells us what happens at primes L dividing n. But they are still, I mean, we are still assuming that primes L not equal to P. Like all of this is happening for L not equal to P. That Grothendieck monodromy theorem and everything, that was only for L not equal to P. That was representations from GQL to GL and QP bar with L not equal to P. So it's not, so here what we have, so the upshot is that now given a new form, we know what happens at L not dividing the level and P. We know what happens at L dividing the level, but L not equal to P. But we don't know what happens at L equal to P. And this is where the subtlety lies. You know, all this grothendieck monodromy theorem and everything, as I said, it relied crucially on the fact that the wild inertia is not causing any problems. Wild inertia is going to is having a finite image. But what happens, what you can say is that when you have L is equal to P, the wild inertia is a pro-P group, and pro-P group can go into pro-P group, right? So whatever argument that we gave that the wild inertia cannot go into pro-P group, that sort of breaks down whenever you have the case L is equal to P. So the wild inertia group, we don't know what it does. And that's why everything becomes very hard. We have to like really see how things happen on wild inertia to understand what is really happening. Because if on wild inertia, if it is trivial, then it's easy, because we know the tamely ramified inertia and so on. But we don't know what happens. We don't have any control on what happens at wild inertia groups. So for that, basically, you have to go into p-adic Hausdale. Whatever we said before, it cannot be used, and then that's a subject of its own. So basically, what happens at L is equal to P, that could be like another semester-long course or even more. So we are not going to go into that. Maybe I can just say that when P does not divide N, the representation restricted to GQP is something known as crystalline representation. So it's a special class of nice representations. However, in some nice cases, we do know what happens at P, and that's what we are going to do next. So we introduce the notion of P ordinary eigenforms. So let F be a new form of level gamma 1 of N. We say that F is P ordinary if one of the following holds. If P doesn't divide N, the TP eigenvalue of F is a p-adic unit. And if P divides N, then the UP eigenvalue of F is a p-adic unit. So basically, if one of these two cases hold, we say that F is P ordinary. And when F is P ordinary, thanks to this theorem of due to Hida and Wiles, we know that the representation looks very nice when restricted to GQP. So let's see. So let F be a P ordinary new form of level gamma 1 of N and bet K greater than or equal to 2. Let epsilon F be the Nebentipus and rho F be the p-adic Galois representation attached to F as above. Then rho F restricted to GQP is isomorphic to this upper triangular representation, eta 1 star 0 eta 2. The nice thing about eta 2 is that eta 2 is an unramified character of GQP, such that eta 2 of rho P is the p-adic root of the polynomial x squared minus apfx plus epsilon p f times p power k minus 1 if P does not divide N. And it is the UP eigenvalue of F if P divides N. So basically, APF is the TP eigenvalue of F. So whenever F is P ordinary, whenever the TP or UP eigenvalue of F is a p-adic unit, the rho F restricted to GQP, it looks nice. It looks upper triangular. It's an extension of a character by another character. And this character appearing at the bottom, eta 2, this is an unramified character of GQP. And moreover, we know the value of rho P at this character. And it is basically the p-adic unit root of this polynomial x squared minus APF of x plus epsilon FP power pk minus 1 if P does not divide N, or it is the UP eigenvalue. So basically, because AP of F is a unit, there is a p-adic root and k is greater than or equal to 2. There is a unique p-adic root of this polynomial. So I should say that we have put k greater than or equal to 2, but I mean, there is a version of this theorem for k is equal to 2. It's just that when P does not divide N, you don't have this nice, eta 2 of rho P cannot be the p-adic root because both the roots are going to be p-adic units. But what happens is that when P doesn't divide N, this rho F restricted to GQP, it is unramified from Deling's theorem. It is just a sum of two unramified characters. And the value of rho P at those two is just like the roots of this polynomial, x squared minus APF x plus epsilon F of P. There's no k minus 1 goes away, right? So a theorem of this sort is also there for weight k equal to 1. So if you just want to remember the upper triangular form, it is there for k equal to 1 as well. And the unramifiedness is also there. It's just that when P doesn't divide the level n, this star is 0 and both eta 1 and eta 2, they are both unramified. So it's not easy to state. That's why I stated this in this convoluted way. So my next topic is actually ordinary families of modular forms, but I don't have enough time left on my, so I don't think I should do this. So let me just skip to my last slide, and then we might come back to this in tomorrow's lecture. So let me just skip. As you can see, there's a lot of things here. So we'll just skip it to the very last slide. That what we did right now is we were talking about Galois representations attached to wide variety of. So we talked about Galois representations attached to modular forms, to elliptic curves, and so on. But in general, we can attach periodic Galois representation to a wide variety of automorphic forms. So basically, it's not just modular forms. This is like an active area of research. Where already we know that we can attach it to many modular automorphic forms, like the Hilbert modular forms, automorphic forms, or unitary groups, and GLN, and so on. And this is like one direction of the Langlands program. And there's still active research to attach Galois representations to some automorphic forms for which we don't know. So the point I want to make is that even though we were restricting ourselves to this prototypical example of modular forms, we can actually attach a periodic Galois representations to a wide variety of automorphic forms. But what do we compromise? So the compromise is that we usually get n-dimensional representations of absolute Galois group of some number field K. So we may not stay over Q, and we may not stay in this nice cozy two-dimensional setting. We may have to go to n-dimensional setting of some general number fields. So for example, suppose F is a totally real field, then, and F is a Hilbert modular eigenform over F, is capital F. Then we can attach a two-dimensional periodic Galois representation rho F of GF. However, this, I should say, so basically it is still two-dimensional, but it is attached to like a Galois group of the totally real field and not GQ. So we are already going to a subgroup of GQ and not all of GQ itself. So that is what we are sort of sacrificing. And in the Hilbert modular case, the properties of rho F are really similar to the periodic Galois representations attached to modular eigenforms. Like for example, if rho F is unramified at primes, not dividing the level of F, so these kind of things, they have many things in common. There are different things which are different, but there are also things which are in common. And also the weight one picture here is similar. You get a representation over GL to C if you have a parallel weight one eigenform and so on. And the next sentence will seem out of context now because I have skipped the Hida families part. We'll come to it in the next time, that we can also define Hida families of Hilbert modular forms and analogs of the theorems of Hida and Wiles. And they also hold in the Hilbert modular form setting. So basically the ordinariness theorem that I stated, the similar theorem is also true for Hilbert modular forms, but it is slightly more complicated. You may have to be in the nearly ordinary setting if the weights are not parallel and so on. But most of the theory that we saw and we will see for modular forms, it will carry over to Hilbert modular forms. So as I said, I'm new to this slide setup. It looks like I put more content than I could cover in one lecture. So whatever that is remaining in this lecture, like the Hida families and the other things, we'll do it in the next lecture. We start the next lecture with that and then go to this deformation theory basics. It fits very well. So I'm going to stop now. There are still like 3 or 4 minutes, but what I have is not like, though this time is not enough to cover that. So I'll just stop here for now. Thank you.
Do you want to take a look at the question? There are a few comments on this. Can these slides be made public soon? It will serve as a good reference to learn these topics. I think they are made available on the website. And then in all the theorems stated, we saw that as the weight of the forms change, there's a change in the involvement in P. Can someone shed some light on the same, that determine whether the condition of weight determines whether P is important or not?
Yeah, I mean, the P is basically, whenever weight is greater than or equal to 2, P always plays a role, right? We have a periodic Galois representation for every P. It's only in weight 1 that the P is not really playing any role. because we are getting a complex representation and we view it at a periodic representation. But otherwise, for higher weights, P is always playing the role. And the determinant is changing because of that. But otherwise, I mean, P is always playing the role.
Shaunak, maybe a point to mention would be that when you take weight 1, it's really what are classically called art in representations. It's closely connected to that.
Yeah, exactly. So that's the complex representations of the absolute Galois groups are called Artin representations, as Professor Sujata mentioned. And these are like examples of the Artin representations. To weight 1 forms, we attach Artin representations. So they have finite image because the topologies don't match, and the representations that we get are continuous.
Sorry, I'm actually interested in one of the questions that was asked earlier on in the chat. It said, what is determinant of rho f for a Hilbert modular form F? So I'm specifically interested in non-parallel weights.
So non-parallel weight, I think what happens is that you take it becomes like the highest weight minus 1 or something like that. You take the cyclotomic, you take the norm and you take the power of highest weight minus 1, something like that happens.
Okay.
I don't remember the formula at the top of my head, but for example, the Hofstadter weights, and when you sum them up, their sum is always like a parallel weight. It becomes something like highest weight minus 1, something like that.
Okay.
So for parallel weight, it's clear, right? It's just 1 times k over k minus 1.
Exactly like over q, but
exactly, yeah. And for non-parallel weight, I think you choose the highest weight, or maybe you sort of normalize that highest weight somehow, and you take its power minus 1.
Okay, thanks.
Okay, there's okay. So let's thank all the speakers in the morning session and reassemble in an hour.